Okay, this is the video about relative rates, but these problems are maybe just a little more involved. But now that we've had an introduction to how to do a relative rates problems, it will be not too terrible. So number 6 says a street light is mounted at the top of a 15-foot pole. A man that is who is 6 feet tall walks away from the pole with a speed of 5 feet per second. That's his rate of change. How fast is the tip of his shadow moving when he is 40 feet from the pole? So here is the situation. Here is a lamppost giving off some light, and here is the ground. And there's a man who is walking. He's walking this way. He's walking away from the street lamp, and he's got a little shadow that's being cast. So here is our light. It is shining on the man, causing a shadow to happen. What we know, what they gave us in this problem is that the light pole is 15 feet tall. 15 feet tall. Okay. And the man is 6 feet tall. Okay. And then they say the man is walking away from the pole with a speed of 5 feet per second. So let's see. Let's call the man, let's call his distance. This is him. He's increasing his distance here, x. This is x. And the rate at which he is walking away from the pole, the man is who I'm calling x, is 5 feet per second. Okay, and then we have this other thing, which is the tip right here of his shadow. And so what they want to know is how fast is the tip of the shadow moving? What is, I'm going to call his shadow distance y. How fast is dy? What is dy dt? Okay, when at the point in time when the man is 40 feet, when x is 40 feet from the pole. That's what we have to figure out here. Okay, so we have to do a little bit of thinking about this. What could we do to get an equation that will relate both of these quantities together? So when I look at this, I see two triangles. I see two right triangles. I see this one. Here's a right triangle, and then I see this one. If we think of the man, here's the man. Here's his right triangle. Okay, so what we could do here is when you hear a right triangle, almost everybody wants to go straight for the Pythagorean theorem, and it's a wonderful formula, but you don't always use that. In this case, what we're going to use is similar triangles. If triangles have two same angles, then all three angles are the same and they are similar. They're the same shape, different sizes. So see, this angle is in both of the triangles. Here's one small triangle, and then here's one big triangle. So we can use similar triangles. We can say, okay, this height, 15, is to this bottom part, which is x plus y, right? Almost called him w. Okay, x plus y. So we could say 15 is to x plus y. This side is to this side. As the smaller triangle, this height, 6, is to this length, y. Just using similar triangles. That's a formula that we can use. In a minute, we'll take the derivative with respect to time. But before we do that, we should simplify this if we can. And we can. So let's cross multiply right here. Let's see, 15y is equal to 6 times x plus y. Let's just do a little algebra. 15y is 6x plus 6y. Let's combine like terms by subtracting 6y from both sides, and we get 9y is equal to 6x. 9y is equal to 6x. That just simplified life a lot more for us. You wouldn't have to do that, but it saves time and effort and room for error. Now we're ready. Let's take the derivative with respect to time. What we get here is 9 dy dt is equal to 6 times dx dt. All right. What did they tell us? They told us dxdt is 5. So we're ready. We're going to say 9 times dy dt is equal to 6 times 5 feet per second. And all we have to do is divide both sides by 9 to solve for dy dt. So with dy dt, the tip of the shadow is moving at a rate of 30 divided by 9, or if I divide this by 3, 10 over 3 feet per second. So that's an example where we had to relate two similar triangles together. Okay, that is number 6. Let's do 7. Number 7 looks like this. It says a man starts walking north at 4 feet per second from a point P. 5 minutes later, a woman starts walking south at 5 feet per second from a point 500 feet due east of the point P. At what rate are the people moving apart 15 minutes after the woman starts walking? Okay, this definitely calls for a little bit of a picture. So let's see if we can diagram this just a little bit. Here we go. A man starts walking north at 4 feet per second from some point P. So this is the point P, and this is north. So this is the man walking north, and his rate is 4 feet per second. So I'm just going to call him x. dx dt is 4 feet per second. Okay. And then it says 5 minutes later, a woman starts walking south at 5 feet per second from a point 500 feet due east of P. East is to the right. So 500 feet away, this is 500 feet. A woman starts walking south. I'm going to call the woman y. And her rate of change, dy dt, is equal to 5 feet per second. 5 feet per second. Okay, so what they want to know is, okay, they're walking, he keeps going, okay, he's going north, she's going south, and so this distance between them, what is the rate of change? I'm going to call this distance z. What is dz dt when? At what rate of 15 minutes after the woman starts walking? 15 minutes after the woman starts walking, but she started walking 20 minutes after he started walking. So let's see, 15 minutes after y starts walking. Okay, this is what we have to figure out. Okay. All right, so first thing that I'm gonna just pay attention to is they said at what point in time is 15 minutes, but the rate of change that they gave me were in feet per second. So there's a little bit of conversion we'll have to do here to make sure we are talking the same language, not minutes and seconds, but seconds and seconds, or minutes and minutes. We've got to do some conversion there. Okay, the second thing is let's just picture what's happening here. There's this man walking this way. 500 feet away, there's a woman walking this way, and so this distance between them is growing and growing and growing. And we need to know what is the rate of change of dz, the distance between them. This is what I decided to do when I was thinking through this. I decided to sort of redraw this picture so I could look at z. So if here's my point P, there is the man walking this way, there is the woman walking this way. But they're 500 feet, so I just sort of dropped this 500 down. I know this is all, 500 is not changing, but what is changing is this right here. This is changing, z is changing. This is x, this is y. And so even though I dropped the 500 down so I could look at this as a triangle, this is a fixed distance. But this is getting taller as these guys go further apart. And so this is getting longer as these guys go farther apart. But I decided to look at it like this, which you are allowed to do. This is a fixed distance. This is 500 feet, okay? This height of this triangle is composed of x and y, x plus y, and then the hypotenuse is z. I am going to use Pythagorean theorem to try to relate all these things together. So let's do this. Let's see. This side is x plus y. So x plus y squared plus this leg, 500 squared, is equal to z squared. That's the Pythagorean theorem, and this relates all of the values that we're interested in knowing. So that's going to be the formula we can work with. Let's see if we can figure a few things out. In order, when we take the derivative, there's going to be some x's and some y's and some z's and some dx dt's and some dy dt's and some dz dt's. So what are x, y, and z? Well, they said the man starts walking at a rate of 4 feet per second, and the woman starts walking 5 minutes later at a rate of 5 feet per second. And so at this point in time, 15 minutes after the woman starts walking. So she's been walking 15 minutes. So let's figure out what y is. 15 minutes, what is y? 15 minutes times 5 feet per second. We need to convert minutes to seconds, so I'm just going to do that here. Times, if I put this over 1, times 1 minute per 60 seconds. This is called dimension analysis. Probably you've done this in math, or certainly in chemistry, I would imagine, or physics. Seconds cancels, minutes cancel, so we're left with how many feet she's traveled in this amount of time. So 15 times 5 times 60 ends up being, let's see, what did I figure out she was? Where did I do that? Yeah, right there. 4,500 feet. She has traveled 4,500 feet. All right, so this is y. That's what y is at this point in time. So we're just going to hang on to that. I might have to erase it to make more room. Let's go ahead and do the conversion. How long has the man been walking? Well, he started 5 minutes before her, so he's been walking 20 minutes. This is x's distance. He's been walking 20 minutes. But let's go ahead. We know we got to convert that to seconds. 60 seconds in 1 minute. Okay. Times his rate is 4 feet per second. Okay. Let's see. These cancel. Seconds cancel. We multiply these numbers together and we get 4,800 feet is how far he has traveled in that amount of time. So this is what x is. This is what y is. This is the formula we need to take the derivative of. So if we take the derivative of that with respect to time, d dt, you know what? I'm not quite ready to do the derivative. Let me simplify this just a little bit. Let's go ahead and square that before we take the derivative. So this is going to be x plus y squared turns into x squared plus 2xy plus y squared plus 250,000 is equal to z squared. Okay, so I just multiply this together. Now let's take the derivative with respect to time. And then I'm going to move it up here so I have more room. d dt of u, of u, d dt of u. Okay, so what happens here? The derivative of x squared is going to be 2x dx dt, chain rule, plus, this is product rule. We have a function of time times a function of time. So it's going to be first, which I'm going to call the first function 2x and the second function y. First, 2x times the derivative of the second dy dt, plus second, y times the derivative of the first 2 dx dt, chain rule, plus derivative of y squared is 2y dy dt, plus the derivative of a constant, which is 0, is equal to 2z dz dt. So that is the derivative of this function with respect to time. Now let's plug in what we know. We know that x is 4,800. So we have 2 times 4,800, and this is feet, times dx dt, which they told us was 4, plus 2 times x, which is 4,800. 4,800 times dy dt, which they told us was 5, plus y, which is 4,500. 4,500 times 2 times dx dt, which they told us was 4, plus 2 times y, which is 4,500, times dy dt, which is 5, is equal to 2 times z times dz dt. Uh-oh, we don't know z. Can we figure out what z is at this moment in time? Well, at this moment in time, x is 4,800 and y is 4,500. So we know the length of this is going to be x plus y, which is going to be, what is that added together? That is going to be, did I write that down? Well, let me just add it together. 4,800, 0, 0, 8, 9, 10, 11, 12, 13, 9,300. So this is 9,300. I can use the Pythagorean theorem to figure out z. So I say 500 squared plus 9,300 squared is equal to z squared, and I get that z is equal to the square root of something, but let me see what I wrote it as. Oh, I said I rounded it to the whole number, 9,313. That's what I did put in there for z. So 9,313 feet, 9,313. This is some algebra. Multiply, 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 multiply. Add those together. Divide by 2, 9,313, and we get that dz dt is equal to 8.99 feet per second. That's what you're going to get when you do that algebra right there. Okay, last problem. Let's do it. The last problem has to do with a water tank that's in the shape of an inverted circular cone. So, again, you're probably going to need to find a formula for this, and I looked at the inside of the book to find the formula for this, and what I looked for was the volume, and the reason I looked for the volume of this was because that's what some of the values that they gave me in this problem that I could relate to each other. So that's what made me go for that. So it said a water tank has the shape of an inverted circular cone with a base radius of 2 meters and a height of 4 meters. If water is being pumped into the tank at a rate of 2 cubic meters per minute, find the rate at which the water level is rising when the water is 3 meters deep. Okay, so when you're doing word problems, if you've done many word problems, you probably know that sometimes, in fact, for me, every time, I have to read the problem more than once, and sometimes I have to read it several times. So anyway, this is how this one goes. It is an inverted circular cone, and so they give us the base of it. So let's draw ourselves just a little picture. Let's draw ourselves a little circular cone right here. Little cone right here. It's a little circular cone. All right, so, and it talks about the base radius. So this is the base, and so it's inverted. That's why I drew it upside down. So this has got a circular base, and so since it's got a circle, it's got a radius right here. So there's the radius of the base, and then it talks about the height of this tank of this, and so this is the height right there. Okay, and so in this case, all right, it says I'm going to redraw it here so I can label it. Okay, in this particular case, it says that the radius is 2 meters and that the height is 4 meters. And you know, when you're taking the height of anything, it's got to meet at a right angle. That's called an altitude. So that's why I drew a right angle right there. If water is being pumped into the tank at a rate of 2 cubic meters per minute, if you listen to the units, cubic meters is a unit of volume. So what they just gave us right there was dV/dt. So dV/dt is equal to 2 cubic meters per minute. Okay, so they gave us something to do with the volume. Find the rate at which water level is rising when the water is 3 meters deep. So what we've got here is, we want to know, okay, so this is height, so they're pumping water into the thing, so it's rising, it's rising, and rising. So if you look at this, the H is changing and the radius is changing with the amount of water that's in the tank so far, okay? So at what point in time, what they say is, what is at the rate at which the water level is rising, what is dH/dt when H is 3 meters? What is dH/dt when H is 3 meters? Okay, that's what we got to figure out. This is what they told us. Now, the formula that's going to relate H and R and V together is going to be the volume of a circular cone. So I looked this up and I got that the volume is equal to 1/3 pi R squared H. So it's close to the formula of a sphere, but it's different. We have this height because it's not just a ball. So the situation here, right here, is volume, radius, height. We've got 3 variables going on. So if we were to, at this point, take the derivative with respect to time, we would have to deal with dV/dt, dR/dt, and dH/dt, which is an awful lot to have to handle. So what I am going to do is try to rewrite R or H one in terms of the other so that I don't have as many things to have to handle. What can help me out here is the fact that they told me the radius, this is R and this is H. Okay, this is for this specific cone. But in general, we have this, and then we also have this water level, H, right here, this little blue triangle. So if we take the big black triangle, we could say the radius 2 is to the height 4, as in the little blue triangle right here, the radius R, and I'll make him blue, is to the height of the water H. And so this is true. We can relate this to each other, but luckily they told us at this point in time where the height is 3, so we can put in 3 right here. So we can solve for R. No, I'm sorry. No. Do not put that in. You don't put the value until after you've taken the derivative. That was a mistake. I shouldn't have done that. As R is to H. This is true all the time. So I don't put in the 3 yet. Go ahead and solve for R in terms of H or H in terms of R. I'm going to cross multiply. 4R is equal to 2H. Okay, so we can solve for R or we can solve for H, one in terms of the other. When I look at what they're asking me to find, they want me to find dH/dt. So really what I want to do is write this formula all in terms of H and get rid of the R, because I don't know what dR/dt is. So let's see. I'm going to solve for R in terms of H. So R is going to be 2H over 4 or H over 2. What I'm going to do is substitute this in for R. So V, I haven't taken a derivative yet. I'm just rewriting my problem. R, I'm going to replace it with H over 2. H over 2 squared times H. So why did that help? Because now I just have 2 variables I have to fool with. And so when I take the derivative, I'll have 2 derivatives, dH/dt and dV/dt, and I can handle that because they gave me some of that information. So this is a good way to go. Let's clean this up a little bit before we take a derivative. So we got V is equal to 1/3 pi H squared over 4 times H. V is equal to, let's see, h squared times h is h to the third. Pi over 3 times 4 is pi over 12. Now I'm going to take the derivative with respect to time, and then we'll see. So if you notice, like I sort of almost made a mistake there. You don't ever plug in the give, like they'll say at this moment in time, what is the rate of change? I almost plugged that number in before I took the derivative, which is wrong. I shouldn't have done that. You always plug in at that moment in time information after you've taken the derivative. So be careful about that. Let's take the derivative with respect to time of both sides of this equation. Goes like this. This is going to be dv dt is equal to 3, this is power rule 3 comes in front, so it's going to be pi over 4 h squared times dh dt. Let's see, what do we know? We know that dv dt is 2 cubic meters per minute. Pi over 4, where do we think h was? H is at what? Oh, they said, now I plug this in. At the moment in time when h is 3 meters, and we're trying to find out what dh dt is. And we can solve this. So this is going to be 2 cubic meters per minute is equal to 3 times 3 is 9 pi over 4. This is meters squared dh dt. If I divide both sides by 9 pi over 4 meters squared, 9 pi over 4 meters squared, I get that right here, dh dt is equal to, it's going to be, if you do a keep change flip right here, 2 over 1 times the reciprocal 4 over 9 pi, you're going to get 8 over 9 pi meters per minute. That's the rate of change of the height at the moment when the height is 3 meters high in the tank.